All right, so the voice is okay. So good afternoon, everyone. My name is Mengting. I'm from UC San Diego. I'm going to talk about item recommendation on monotonic behavior chains. This is a joint work with my advisor, Julian McAuley. Oh, here we go. So we know the implicit feedback, explicit feedback. So these are two very important topics in recommender system. Ideally, we want to collect some explicit feedback, like the rating scores, which explicitly reflect users' preferences. But providing such kind of feedback is relatively tricky because it may require additional cognitive effort. So this kind of feedback is relatively limited in terms of quantity. On the other hand, we probably have much more implicit feedback where the user preference can be reflected through their real actions, such as a clicks action, purchase action, and so in terms of quantity, we have a lot of more implicit feedback. So these two kinds of feedback usually studied like as a two relatively isolated areas for years, but in real-world recommender system, what we will see is we're going to see a spectrum of different kinds of user feedback. Like in this e-commerce system, we're going to see a user comes in, click a product, purchase a product, and when user got the product, left a review. Based on this review rating scores, we can decide whether this user going to recommend this product, like this product or not. So a natural question is, we want to do item recommendations based on all of these kind of feedbacks, but how to properly represent a spectrum of these users' responses, and also how to efficiently leverage the connections between these different types of responses. So our view here is we find in a lot of cases, users' different types of feedbacks can be aligned on a behavior chain. In this case, we see a user click, purchase, review, recommend. So this is a behavior chain. A very interesting property of this kind of behavior chain is this monotonic constraints. So we see that any signal necessarily implies the presence of a weaker or more implicit signals. Like this review actions implies a purchase actions and implies a click action. If you observe a user purchase the product, so this user has to click this product, has to view this product. If you observe the user didn't purchase a product, so this user won't be able to left any review or rating scores. So, and also this user item interactions can be encoded as a binary state on this behavior chain so that we have this kind of a binary tensor. Basically, for each user, we have this item dimension, interaction stage dimension, and for the highlight vector, this 110, it means the user clicks, purchased, but didn't review or recommend this product. And because of the monotonic constraints we have observed, we can see for each user, we have such kind of binary matrix, which starts with the most implicit but densest stage, which is click, and ends with the most explicit but sparsest stage, which is recommend. So our goal here is given historical interaction matrix, we want to estimate users' response to the unobserved items by leveraging this kind of monotonic constraints. So we can approach this problem by investigating some standard conventional learning strategy. First, we can consider learning user preference independent of stages. Basically, for different types of feedback signals, we train different kinds of model. We train a matrix calculation for clicks. We train another matrix calculation for rating score. Definitely, it's going to ignore all the stage dependencies we have. So we can consider, like a matrix calculation, we have item embedding, user embedding. We can share the embedding across all the stages and then train a big model on all the stages. So it's a joint training. But this kind of learning strategy doesn't model this monotonic structure we have observed directly. We can also consider train condition on previous stage. Basically, we train on this stage escalation, like in order to predict whether user want to purchase a product, we are going to collect all the items they clicked, and then we do this prediction. But the problems here, we can see this conditional training gonna gradually narrow down the training scope. So at the later stage, at the last stage, we only have 2 examples for training. So if we only have 2 examples, then the model may be not very reliable based on just such limited training data. So the problem is the scarce data at the later stage. Now you can forget what I have said about the previous slides because we are coming to the most exciting part. We propose a new algorithm, which is called ChainRec. We propose 2 techniques here. One is called a monotonic scoring function. Another is edgewise training. So monotonic scoring function is proposed to preserve this monotonicity in the interaction matrix. And edgewise training is trying to remove all the redundant information and improve the optimization efficiency. So we can look at the monotonic scoring function. We observe this monotonicity in users' feedback in the label. What we want to do is we want to preserve these monotonic constraints in the predicted user preference scores, because we always want to use the preference scores to approximate the label we have. What do we want to do to achieve this? We want to look at the difference between 2 preference scores, this S1 and S2, and we want to make sure the difference is non-negative. So we are going to model the difference between 2 scores directly. The trick here is we want to first do the tensor decomposition. This is very similar to the matrix creation idea. We learn a user embedding, an item embedding, and also a stage embedding. We do the itemized multiplication about the item embedding and user embedding. We use stage embedding as a scalar. So we got a sort of like a score delta. But we cannot make sure this delta is not negative. So we pass the delta into a rectifier. So the rectifier is going to keep the positive part of delta, but it's going to rectify the negative part of delta to 0 or close to 0. So we treat this delta plus as a difference between these 2 scores. So at the end, we're going to get this explicit format about monotonic scoring function. So so far we have done about the monotonic scoring function. We have already applied our monotonic constraints. But we don't want to double count it. We want to train this model smartly. So the way we want to train is called edgewise optimization. We're going to revisit these monotonic constraints we have so far. If you look at the equation, what this equation tells us is what really matters is the shaded cell, the values in the shaded cell. If the shaded value is equal to 1, it actually already implies all the labels for the previous stage have to be 1. That's a monotonic constraint. If we know that this shaded cell is 0, it actually implies all the following stage, the labels of the following stage have to be 0. That's a monotonic constraint. So what really cares is actually in this edge area. We just train the models in this highlighted area, and it's actually, we just do a few like mathematical deduction, and we can see in the loss function, what we really care is the very last positive stage, the very first negative stage, and the mutual information at the edge. So we can conclude all these techniques in this algorithm. It's very simple, actually. For each positive item for each user, we are going to locate the last positively interactive stage. We update the associated parameter. That's actually is a monotonic scoring function comes in. Then we're going to sample some contrastive examples. We're going to locate the last non-interactive stage and update the associated parameters. So we apply this algorithm on 5 different data sets. For each of them, we're going to have sort of like a behavior chains. For Steam data, it's a video game data. We have this purchase, play, review, recommend behavior chain. You choose is a RecSys challenge data. This is e-commerce data. We have this click purchase behavior chain. Yelp, Google Local, those are 2 standard review data sets. We can set a threshold based on rating score so that we can get this review recommended chain. We contribute a new data set, is Goodreads. This is an online book review data set. We have a shelf. Shelf means a user going to add a book into his or her virtual shelf, bookshelf. Basically indicates this user is interested in this book. And we have this shelf, read, rate, recommend behavior chain. So applying the algorithm, we'll compare our algorithm with several baselines. There are 2 groups of baselines. One is the first one is a standard recommendation baseline, but it ignores on the stage dependency. We also consider another group of baseline which incorporates the stage dependency, but not really exactly the same as the one we propose to model the monotonicity. And we can see our proposed model can achieve the best results almost across almost all the data sets. So to conclude the work, we propose this concept of a monotonic behavior chain, and we propose a smart algorithm chain rec, which use two particular techniques. One is monotonic scoring function, which is trying to preserve this monotonic constraints. Another is edgewise training, which actually is used to improve the training efficiency. And for the future, we consider a chain structure here, but actually this work can be extended for the other structure, like a tree structure. So we can also consider the features and the counts of interactions, like for the music recommendation, we have the play counts, and for the purchase this transaction, we also have the counts of purchase. We can consider them as a confidence of the behavior, and it can be applied in other areas such as medical diagnosis. So thank you.
Thanks very much. So it seems like with tree rec, if I can like read your mind, you're sort of thinking that like, oh, if I just have like any totally ordered set, I can sort of do this thing. Does this extend to like if I just have a set of actions and then just like a partial ordering? Like maybe I've got like I can click and then do stuff, but maybe I can also fill out a lead form and then do stuff, and also call and do stuff, and there's only like a partial ordering.
Yeah. So I think even for the tree rec, I think the primary techniques also it can be decomposed into several chain rec. So tree rec might be a more general structure, and we can also extend this kind of techniques to like different kinds of branch. Yeah.
Awesome.
Hi, I've got two questions. The first question is that you're talking about different signals at different stages. Mm-hmm. Did you also try to do a weighted combination by learning them separately?
Yeah, so we actually compare like two groups of baseline. So the first one is like this is a evaluation results based on the most explicit stage. We actually evaluate for all the stages, and we include the results in the paper. So the first group is we train them differently, we train them independently. We only train the data on the last stage. The second group is we consider some alternatives, which also use basically the same information we have, but use different kinds of training techniques. And we can see that the proposed method is train rec, it performs really good. It can beat like this. We train each stage independently.
Okay. The second question is around the sparsity as you move along the chain. Most of the data sets had, after first action, the sparsity did not reduce too much. Do you have any take if the sparsity decreases after purchase? For example, users don't review too much or users don't rate too much.
Yeah,
how does that work out?
That's a very good question. We didn't do this systematically to evaluate the relationship between the performance and the sparsity of the data set, but empirically speaking, when I implement this algorithm and do the experiments, we find that it works pretty good for those sparsity decrease very much, especially on the last stage. But for very relatively dense data set, somehow you don't need to enforce this kind of monotonic constraints because the data already tells you there's some sort of like monotonic constraints here, but you have enough data, you can train a model, you have enough data for training, so you can train them either independently or jointly. So that's some like empirical results, but yes, that's a very good idea. And I think for this kind of chain rec, it's just an initial study. This kind of chain rec method, we also plan to do sort of like a theoretical study about this kind of optimization method, and when it's kind of work, like you said, it might be related to the sparsity of the data or the sparsity of the behavior escalation. Yeah.
Thank you.
So, hello. A very quick question that I think you might have answered in what you were saying right now. So I noticed that in the paper you were saying that chains that were supposed to be monotonic are not in the data set. So people rate things that haven't watched or haven't bought or whatever. What did you do in the experiment? Did you just impose monotonicity and you just remove that data? Or do you have any other approach on what to do in these cases?
Yeah, so in this study, we just focus on this monotonic behavior. So make assumption that this monotonicity is true by nature, at least in this data set we're considering. But like you said, yes, in real world cases, there might be some noisy things happened. Sometimes we're gonna miss some, we see this user purchase a product, but we didn't see it in the click logs. But in this case, we're gonna fill in the click data as true. But actually in our algorithm, if you look at here, it actually doesn't matter. What we care is as long as the edge is accurate. So what happens before this is true, is not explicitly utilized in the optimization process.
Okay, thank you.
Good.
Okay, thank you.
Good.